Okay, so basically till now we were discussing about simple current mirrors. Now we'll go one step ahead and we'll try to have some sort of advancements in the current mirror, and that is basically known as a cascode current mirror. Now, what is the usage of cascode current mirror and why do we require everything we'll try to see. I'll just forward this document also at the end of the session. Okay, basically let's try to understand why or what is the glitch that is involved in the current mirror. So we have this kind of circuitry where we had two MOSFETs and you had a reference IREF being connected over here, and we were expecting an I output over here. And when I say this is M1 and M2, yeah. Now this was our simple current mirror. Okay, where we ensured that current IREF over here is exactly mirrored and can be reproduced at the output based on the scaling factor. And what is my scaling factor? It is W by L ratio of this and W by L ratio of transistor number 1. Now the issue or the challenge that is involved over here. Now when we try to build a simple current mirror, everything looks good yesterday and we are able to closely get some sort of approximately, if I consider a reference current of 100 microampere, we closely got near to the 100 microampere of current. But usually when it actually goes to the actual real-time circuitry, when we actually go into the industry standard, we always have to consider MOSFET as a practical entity and not a theoretical entity. What does that mean? See, basically, the ideal ID current equation in saturation region is given by what? 1 by 2 mu n C ox W by L VGS minus VT whole square. And we do not consider the impact of lambda, that is channel length modulation, is always ignored, and that's why you never see VDS term in the ID equation. And your current mirror is all, whatever you design, it is purely dependent on whether the MOSFET is biased in the saturation region or not. And if my MOSFET is biased in the saturation region, what does that mean? That means a constant current is flowing during the saturation region of operation. And that also means that the graph would be of that particular current would be looking something like this. And that also means that this current is not a constant entity, it is having a small incremental value, and that will give rise to finite output resistance R naught, and which is accounted for the term, or which is accounted by the term lambda. So basically in the drain current equation, I cannot directly model or run the simple current mirror circuitry without the implication of lambda. So that's the reason whatever the design we did yesterday, because what was the thing, IREF current is given by the same equation and I out current is also given by same equation. Everything will cancel out and only W by L ratios will be deciding factor. That will be the scaling factor. See, basically when we did when we want to calculate the current gain, we said that I out divided by IREF, and all the formula is going to remain same. The current equation is going to remain same, and all the terms will cancel out, and only what will remain? It is the W by L ratio, W by L of 2 divided by W by L of 1. Why everything will cancel out? Because everything is same, because VGS is same, because the VGS of M1 is same as that of M2. And here you have not considered VDS, and there is no question of VDS coming over here. But practically, we have to consider the notion of or the implication of VDS also. And how do we consider the implication of VDS? By considering the channel length modulation implication, or by including the small finite output resistance that is observed in the saturation region. And by that notion, my current equation would now be changed into equation number 1 and equation number 2. That's how my current equation would now look like. So ID1, 1 by 2 mu n Cox W by L of 1 VGS minus VT whole square. Now I cannot ignore the lambda, so that lambda has to be included. And how do we include? It is included by the term 1 plus lambda VDS, or just lambda times VDS. That is how it is included. Okay. Now ID1 is basically your, I can say, IREF, and ID2 I can say it as I out. Now let's say that if I want to calculate the current gain, I out upon I ref, if I do, which is nothing but ID2 divided by ID1. Now if I do it, W by L of 2, W by L of 1, they are different, they will remain same. 1 by 2 mu n Cox, they cancel out. VGS minus VT whole square, they cancel out, because VGS is the same VGS that you have applied over here, because the VGS of this and this are being connected. Now the question is whether VDS of Q2 or the MOSFET M2 and VDS of M1 are the same. If you observe over here, you can consider point number X and point number Y. Whether the voltages at X and Y are the same. Now the answer to this question is definitely they cannot be same, because the voltage X here, which is nothing but my VDS value, is decided by this current source and what VDD you are supplying, and whatever drop occurs, whatever value you get, that will be your VDS, which is marked here as X. What about Y? Y here we can have any analog block, and the current or the voltage drop that happens through that analog block or through that entire any block, that will be decided, that will decide the value of VDS2 or Y. That means my VDS1 and VDS2 are not same, and I cannot cancel out, and my entire current gain would now look like this. That also means that there is not proper mirroring. How? Why? How there is not proper mirroring? Let's say that, let's assume that 1 plus lambda VDS value comes to be, let's say, some random value. Let's say it comes to be around, let's say 2, or let's say 3. Let's assume some VDS value is there and it get multiplied with lambda and plus 1, it comes to be around 3. And let's say 1 plus lambda time VDS1 would come around, let's say 4. Now again, these are assumption, any value can come. Intention is I'm just telling you the I out will never be equal to I ref. That is what I'm going to tell. Earlier what you did, you just made W by L ratio of second transistor and first transistor. If they are made same, then definitely I out would be equal to I ref. But right now this parameter will come, so this means it is 0.75. So basically what will happen, I out now will be equal to I ref times W by L of second transistor by W by L of first transistor times 0.75, some number. But this you can cancel out, making them as same, but this will have implication. Now IRF times 0.75 means IOT is lesser than the reference, so basically there is a glitch. Now this is one possibility, and another possibility would be this number may be greater than 1 also sometimes. So which means again that time also IOT is not getting, if it is greater than that, definitely the upper portion is clipped off, and again I'm not able to have that same sort of mirroring. And that is the reason we go for cascode current mirror combination. And in the cascode current mirror combination, so let's say that I have marked over here, like I have written over here, the VDS of 1 and VGS1 and VGS2, these all are equal, isn't it? Because the same node is connected over here and that is also connected over here. That's what I mentioned here. While VDS1 is equal to VGS1 and that is equal to VGS2, VDS2, which is over here, VDS2 is below here. Just a moment, I'll drop it. Yeah, VDS2 may not equal VGS2 because of the circuitry fed by the M2. M2 is being fed by some analog block. Here I have taken a simple MOSFET. There could be a bigger block above this MOSFET. Right now I have taken a simple MOSFET. The simplest circuit is a single MOSFET. So here there could be any MOSFET. So that will decide my VDS2. Because for mirroring to happen, look here, for mirroring to happen, VDS2 and VDS1 also has to be same. Then only I can cancel out these two things, and W by L of 2 and W by L of 1, I can make them same. And then I can say that my I out is a copy of my reference current. But right now, there is no way that I can say VDS2 is equal to VDS1, because VDS2 is decided by the upper block. So that means the voltage at point X is not equal to voltage at point Y. So in order to suppress this entire glitch, please remember this is very, very important concept. The question is, what is cascode current mirror amplifier and why do we go with that? So you have to explain this with the help of this diagram. So in order to suppress this channel length modulation effect, a cascode current mirror can be used, because this voltage VDS2 or the voltage at point Y is not same as voltage at point X. Now, how do I do that? Now, I have taken this circuitry. So this is a cascode current mirror where you can see the two MOSFETs, M2 and M3, are being stacked one over the other. That the stacking of MOSFETs one above the other, that is called as cascode or cascoding. So what I do over here, so here basically I'm considering one simple M3 MOSFET. So basically how exactly it works. So let's say, so this is, let's assume that this is my simple MOSFET current mirror, and here is my analog block. So what I do right now, I'll just remove or switch this analog block to little bit above and add one MOSFET, M3. Now this M3 MOSFET will help me in figuring out the, or in making the value of X and Y to be equal to same. How? Let's try to do that. I'll add M3 and I'll give VB. What is this VB? VB is a bias voltage. Let's try to give this way. That is your VB. Let me take, yeah, so that's your VB. Okay, and what will be your VGS? VGS is nothing but the voltage exactly that falls between the gate and the source. So here is your G and S. That is your VGS. Okay. So what I'll do, I'll add this particular MOSFET with VB, or I can say some voltage, bias voltage, such that I'll make Vy is equal to Vx or Vx equal to Vy. And then I'll track my I out. How do I do that? You can see over here. I have just mentioned over here. Yeah. So in order to do that, what I'll do, I'll see to that this VB, and if I apply a loop equation over here, VB minus VGS3, whatever I'm going to get, if this drop over here, VB minus VGS3, if that is equal to this voltage, Px, then I can say that my Vy will be same as Vx, because what is ultimately Vy? How do you calculate Vy? Vy is basically, see, it is something like this. Let me just give you over here. If I apply a loop equation over here, your entire loop equation concept and all those things, you have to ensure that you remember that thing. So this is basically your node Y, and I'll use another marker. I'll carefully write over here. This is VGS3. So if you apply KVL over here, how do you write? VB, this is plus minus, plus VB minus VGS, and VY will be here plus minus. See, basically if I consider here as a node Y, and how do you take that? It will be like this, right? I'll remove this thing. Or, yeah, right? So if I apply KVL over here, it will be plus minus. So minus Vy. So ultimately, what is that means? That means Vy is equal to Vb minus VGS3. And we need to ensure Vy is equal to Vx, which implies Vb minus VGS3 must be equal to Vx. Or since Vb is in my control, Vb is equal to Vx plus VGS3, and that's what has been written over here. So if I somehow make sure my bias voltage of M3 transistor is equal to Vx plus VGS3, then my job is done. I can say that Vx is equal to Vy, or VDS1 is equal to VDS2. So this is basically going to ensure that my practical current mirror is obtained and there is no drop in the gain of the current mirror circuit. And as a matter of fact, now, so now, like here, how do, so now here, but now this X voltage, whatever you are seeing over here, that is again dependent on IREF over here. The moment you change IREF and VDD changes, this X changes, and again repeatedly you have to keep on sizing this M3 so that your VB is equal to Vx plus VGS3. So again that means there is a huge dependency. Hence, in order to overcome this glitch, what I'll do, I'll try to fix up one more MOSFET in this manner, such that my X is controlled by this M0. My X is controlled by this M0. And then when I fix up this X, I can always fix up this Y. I have already figured out the formula. And this results into a complete cascode current mirror with the modifications to generate the bias voltage. So what I did over here, instead of using this VB as an independent voltage, and because this Vx is now here is totally dependent on VDD, what I did, I add one more MOSFET over here, and through that MOSFET I'll attach this gate to this M3, which results into this thing. So this would ensure that I'm able to see a proper modification, and possibly this modification I'll ensure that VGS3, or basically Vx is equal to Vy. My ultimate goal is to see make sure that Vx is equal to Vy, and that can be done by sizing, because see, this has to be constant. If this has to be constant, see, what was the Vb value here? Vb value was some constant voltage you applied, and that has to be constant, and that you anyhow apply. But Vb, because you are applying as an independent voltage source, it is prone to get affected with the increase in the temperature. So what I did, I'll attach this VB to particular MOSFET in this manner, and I'll also try to fix this X value such that the value of X is always decided by this MOSFET, and this MOSFET W by L ratio is always fixed. Hence, what I can do, W by L ratio of 0 transistor and W by L ratio of third transistor, if I make them same, the current here is same. Depending on that current, the constant voltage is provided over here. That constant voltage will ensure that Vy is getting some value, and the same value Vy is being populated here as Vx. So thereby Vx is equal to Vy. So what I can do, W by L of 3 divided by WL of 0, that should be again equal to these two things, because same X is flowing over here, the same X voltage is Vx is being populated over here, and same Vy is getting populated over here. And by making this entire scenario, I can ensure that your normal or simple current mirror can be built more rigidly or more efficiently. So that is the intent of this entire exercise. So now, based on this entire exercise, I have already built the simple current mirror with the cascoding approach. And now here, our job is to see that can we repeat the entire exercise one more time? So this was your yesterday's current mirror where you had only one MOSFET through which you are generating the reference current. Now here you are cascoding them together. Now here yesterday, whatever the ratio I kept it as 1 micro by 1 micro, and I'll keep the same ratios, because what is the intent of this entire exercise? All the transistor ratios should be now same. Let us try to keep them same so that I'm going to get the reference current properly. So let me just change this to length to 1 micro and width also to 1 micro for all the MOSFETs. Or even I can keep 10 micro by 10 micro also. Anything is fine. Let's do that only. Yeah. So this is 10 micro by 10 micro, 10 micro by 10 micro, and everything is 10 micro by 10 micro. Yeah, there you go. Fine then. So rest all of thing here, a DC reference current of 10 micro is applied. You can apply 100 micro also. And here again, you are applying a VDS DC voltage as a variable, and you are plugging in the AC magnitude. This will ensure that AC magnitude will ensure that to calculate the output resistance. Let's repeat the process. So just let it be. I'll launch new aerial window. I'll get it from the cell view, and I'll make it as 900 millivolts for VDS. And I'll go to the analysis. First, I need to find out what is the output resistance. For that, I need to do AC analysis. I'll go from 1 to 1 gigahertz. You can keep the sweep as automatic, or you can make it as logarithmic. That's not an issue. It will automatically take the log scale only. And outputs to be plotted. Now output to be plotted, the drain current will be here. Yeah. So NM3, if you see over here, this is NM3, and the drain current of that NM3 MOSFET is being chosen. Now let us use it new window and let us run it. This will give you a plot of ID versus VDS in the log scale, and you want to take the reciprocal of that to obtain the resistance. And I'll go to function 1 over x. Sorry, came 2 times. Yeah, so I'll just run it. There you go. Now there was some. Now you can see there is some issue. We'll try to address that. Why that issue? I'll also talk about that. But this is the process. Now the resistance is 347 mega ohm. Now why this instability occurred and what is the reason? The reason is yesterday we did this entire exercise by taking what was the current mirror W by L ratio. It was 1 micro by 1 micro, right? Now here we took 10 by 10, and I reference as 100 micro. So let's try to do the changes. We'll go with 1 micro by 1 micro, and then we'll see whether we'll be able to see a proper output resistance. Yeah, and this reference current, let it be 10 micro only. That won't impact. We'll just close this thing. Yeah, so now everything is set. I'll run it one more time. I'll send it to the calculator. Go to the function, take 1 over x, and yeah, it got, let's see whether it has, yeah, it has got a little bit shifting. Right now, if you see, the dip is somewhere around at 1 kilohertz only, the resistance was dipping. Now here you shifted it to almost to 140 mega, sorry, 56 kilohertz. If you see, I'll just mark it. The marker says that the 346 mega ohm of resistance is observed at exactly 1 kilohertz. Now here, if you see, the 32 kilohertz of resistance is observed at 141 mega ohm of resistance is observed at 32 kilohertz. Of course, the resistance got decreased, but it is across a wide range of frequency. So that is basically due to the reduction in the W by L ratio. So that one thing you can consider. Another thing here, what we can do is, we did this one, right? So now let's try to do the DC analysis and figure out whether the current is getting replicated properly or not. Of course, it has to replicate. Save DC operating point, component parameter, select component. You have to choose this DC voltage, that is VDS. Say OK. Come back to the, let me close these things. Yeah, come back over here. Sweep range from 0 to 2 volts. Why I am taking 2 volts? Because 2 volt is the voltage which is acting as my VDD. So this is my, there is one. So this is my DC analysis. I'll remove this and now I'll plot ID versus VDS graph, which should tell you in which region, or basically, yeah, there we go. Exactly 9.998, and this is seen constantly, it is seen, and this is a great thing, because yesterday what we observed, it was having slight incremental change. Let me just plot that also. Let me just run that. This is yesterday's. I'll change this value from, just change it for some experimentation purpose. I'll launch ADL for this. This is yesterday's, and I'll change the reference current also. Let me change the reference current. Let me just relaunch the ADL window for yesterday's block. Yeah. And let's try to do the DC analysis for this also. Save DC operating point, component parameter, select component, VDS, select DC voltage, say OK. Go back to this ADL window, 0 to 2 volts. It won't impact much, but the reason here why I'm showing is the more stability, because more and more you get into the realistic circuitry, you may feel that this entire current mirror needs to be done on based on the cascoding concept. Let us run it. Yeah, if you observe, it is slightly slanting, right? Right, see if it is, there is a, it is not constant over the entire range of frequency. And okay, that graph got replaced. Okay, let me just now let me just launch this one. You'll get a clear idea. Yes, this is the current mirror with a cascading impact. That means across the entire VDS, my current is it is exactly getting replicated. And here if you observe, it is not the same. It is having slight glitch in the output current, and that is mainly because of the drawback of the finite output, basically due to the channel length modulation impact. So that is the intent over here, right? So you can just do that observation when you do the simulation. That was the one thing. Let me close all these things. This is current mirror, this is cascode current mirror, and this is current mirror. I have two separate ADL window. Okay. Yeah, so that is one thing. Another thing, we figured out the finite output resistance also. Okay, now let us try to mark the value of current. Like for example, here, if you observe, this is cascode current mirror, and if I run this, let me run this one more time. Yeah, I'm seeing this value, but at what particular voltage should I see? I should see this voltage at what value of VGS? If you observe over here, 951 milli. Are you seeing? this 951 milli. So that means I'll use the marker V and I'll put it here as 951 milli represented here, and I'll mark the voltage 9.998, very close to the reference current. That is exactly, you can say 10. So that is the beauty of cascode current mirror. So that is basically your second objective, right? So now once this is done, we need to find the region of operation also. Region of operation is definitely, it will be in saturation only, but let's try to plot the region of operation the way how we did yesterday. So let me close this ADL session of current mirror, and I'll just keep the ADL window of my cascode current mirror. And here, what is that I'm supposed to do? I need to go to the outputs. I'll again do the procedure one more time. Now here, this time, I need to find the region of operation for two MOSFETs, because there are two MOSFETs over here. They are cascoded, right? Here there are two MOSFETs are being cascoded, NM3 and NM1. So I need to find the region of operations for both. So I'll go to output, setup, name. I'll first go region of operation of upper ROPU, and in the expression I'll open the calculator, and I'll just clear all the buffer. I'll click on the OPT. It will get you the list, and you have to select the upper MOSFET. In that upper MOSFET, once you select it, go and select the region. There you go. And come back to this setting. You say get expression. This expression is coming over here, right? Or you can just say here from this only, you can say add here. If you say add here, it will be pushed into ADL window. Or you can come here, get expression. You can click onto this and say add. See, this expression is added over here. The difference, I'll tell you the difference by using the add expression from here and add expression over here. Here, see, it will just add the expressions in the backside, but here the name of the expression will be only shown. See, what was the name of the expression? ROPU, right? See, this is through this output window. When I say add expression, it added the name of the expression. Now let me just do the same entire exercise. Yeah, now let me just go and do this repeated exercise. I'll go to the output, setup, ROP down. Okay, I'll open the calculator. I'll clear these things. I'll click on, I'll redo things. I'll open the calculator. I'll click on the operating point. Now ROP down. So I'll click on this MOSFET. Immediately after clicking on this MOSFET in the list, I'll click on the region. Yeah. Now, what was the difference I did last time? I said here, I said get expression. Now I don't do get expression. I'll just say in the calculator only, I send it to the ADL window. Now, if I do this thing, if you go to this ADL window, see here, the expression itself is pushed over here. So that is the difference. Now here, when you push the expression itself, you will be in a, you'll not be in a position to understand whether this is an upper transistor expression or lower transistor expression. Of course, you can make out based on this transistor name, but it doesn't look neat, right? So that's the reason why I'll say here get expression, right? So when you do this get expression, you'll get that entire thing. And when you say add, sorry, I need to repeat it once again, right? So yeah, that is the difference, what I was telling. So operating point, let me just clear these things. Operating point, lower transistor, list is there, region. If you are getting any confusion, just ignore it and repeat it one more time. That is the only thing. And oh, sorry, I couldn't do it over here, right? So I have to go do it from here. Oh, let me just cancel it. Close the calculator. Outputs, setup, ROP down, open the calculator. operating point, down transistor. In that list opens and I'll choose the region, and then I'll come back to this thing, get expression, and I'll say add ROP down. Say okay. I'll then remove all these things. Now, if you observe, yeah, here ROP up and ROP down. So I'll just delete this one. So this would look nice. Now let us try to run this. Okay, sorry. To run it, I need to do the parametric analysis, right? So I need to go to tools, parametric analysis. I've already added the variable. Variable is the VDS. It will be swept from 0 to 2. Step mode will be linear steps, and step size will be 0.1. I'll say okay. Now, because there are two transistors are there, it will take little extra time to simulate it. Now, this particular entire exercise is close to a mini project itself, and I'll, in the due course of time during the weekend, I'll be floating you multiple assignments and mini projects. Try to work on to this current mirror. That would get you a great values. Yeah. So if you see, the red one is upper transistor and the down one is the lower transistor. And now if you observe, if I place my cursor over here, 2. So my down transistor, which is my yellow line, it has already reached the saturation at exactly what voltage? So if I just mark the vertical line. So at 392 millivolts only, the down transistor has reached the saturation region. But my upper transistor will reach the saturation at 708 millivolts. That means my entire activity of my current mirroring is decided by the upper transistors, because if you observe over here, both my upper and down transistor has to be in saturation together. If you observe at point V1, like if you see, only yellow line has reached the saturation. That means only the below transistor has reached the saturation and not the above transistor. Whereas here, both above and below transistors, if you see, the marker is clearly telling 2 and 2. Red is also 2, yellow is also 2. That means it is exactly meeting the specification. Whereas here, if you observe the other way around, here clearly only yellow line is coming to the 2 volts, because it is not coming, the other thing is not coming, right? So that's the impact, or that is how you can figure out at what particular voltage of VDS your both the transistors will be in saturation region, and this of course is your drain current value. Okay, so this is it from this entire session. I hope you have got some inputs onto this. Try to work on to these things. I'll float a few mini project and assignments on, especially on current mirror. And the next session we'll have one more current mirror, which is low voltage current mirror, and we'll work on to those things as well. And post that, we'll get into what is known as your amplification concept. Okay, so that is it from my end.